So now I start. Okay, so I'm Liangjian from IHAP. Now I'm going to introduce you the neutrinos. So the title is about prospect. But actually I will cover a little bit of history and the current status and also talk about the future. Okay, so this is the I call it a particle universe. And in this plot, probably you're already familiar with, the neutrinos are participants and witness to the origin and evolution of our universe. And if you look at this plot, the density of neutrinos is just less than the density of photons. It's about more than 300 per cubic centimeter. And in the early stage, when the time is less than 1 second, the neutrinos heavily interact with the quarks leptons. So the whole universe is kind of equilibrium. And when the universe starts cooling, and then the neutrinos kind of escape the thermal equilibrium and become slower and slower. So in this case, as a universe cools to this stage, the neutrinos becomes at this stage, the interaction is not so strong, so that the hydrogen start to form, and then the neutrinos becomes even slower. So in this case, in this stage, it will produce the cosmic microwave background radiation, which you already heard in the previous talks. And as time goes, the neutrinos become even slow, becomes how to call it, relativistic. And then the big structure, the larger scale structure starts to form. And now we are here today. So you see in the whole evolution of the universe, the neutrinos play a key role in the whole history. So this is the spectrum of the neutrinos in the universe. And this is the energy, and the y-axis is the flux. And the color in black has been observed, and the color in blue are the neutrinos we are going to found. So these are all the neutrinos from different activities in the universe, and also they are the tools for us to study the properties of the neutrinos. And usually we talk about the properties of a particle. We go to the PDG and see the properties. So, but if you look at the property of neutrinos, most of them are concrete values. Is the either upper limit or lower limit. It's because it's very difficult to detect neutrinos and study its properties. Till now, what we understand is that the neutrinos are massive, but they have very, very tiny mass. So this is obviously the only phenomena beyond the standard model. And we don't know the absolute mass, and we don't know the origin of the mass. So this is something we are going to study in the future. And neutrinos is the only neutral fermion in the universe. And I will talk about later that we don't know whether it's its own antiparticle yet. We call it Majorana neutrinos. Okay, so there are many problems with neutrinos. I categorize it into two different categories. So one is particle physics related. As you see, we don't know we are now using neutrino oscillation to study the property. And we don't have a very precise measurement of the neutrino oscillation parameters. And we don't know the mass ordering. We don't know the CP violation. We don't know if neutrinos are Majorana particle. And we don't know the absolute mass scale of each neutrino. And we don't know the magnetic moment, and we don't know the electron moment, dipole moment. So these are all particle physics related. And the neutrinos can also be a tool to understand the astrophysics and cosmology. And we have the supernova explosion, and the neutrinos will carry the 99% of the energy of a supernova explosion. So using neutrinos, we can understand the mechanism of a supernova explosion and compare it with models. And the solar neutrino produced from fusion inside the sun. And using the neutrinos, we can study the so-called metallicity of the core of the sun. And we also have the uranium thorium decay in our Earth, in the crust, in the mantle, and in the core, and they all produce neutrinos. So using neutrinos, we can study the inside of the Earth. And we are looking for the neutrinos produced from extreme astronomical phenomena like neutron star merger, AGN, gamma ray burst, etc. So we are looking for the neutrino signals accompanied with this very active extreme event to study the astrophysics. And we also don't know, we did not detect the relic neutrinos from the Big Bang. And this is something Weinberg proposed in 1960s to propose the way to detect this Big Bang neutrinos, but we never observed it yet. So these are all the problems. But in this talk, I will focus on the particle physics-related problems, especially the oscillation and the mass ordering, neutrino, Maran neutrino, etc. I will skip this part. Okay, so to study the properties of neutrinos, you need good technologies. And I took this diagram from Yifang in TIP conference. So the top layer is the problem, the neutrino problems, mass, Maran nature, etc. And these are the sources we can use to study the neutrino properties. And the bottom is the technology, different detector technologies. So you see there's a complex relationship between the problems, the means, and your physics goals. So I hope that in my lecture, I can guide you to think about if you are going to solve a neutrino problem, what's your physics goal and what's your what interaction process you are going to use. And based on this, what detector technology you are going to choose and how to build your detector, and eventually how you translate your physics goal into the specification or requirement of your detector, and eventually you can make it and to fulfill your scientific goal. Okay, so here's the outline. I have two parts. Thanks to the previous speaker, I have more time to digest my slides for you. And part one, I will talk a little bit about the history on the neutrino studies and cover the oscillation experiments in the past, in the current stage, and in the future. And also in the second part, I will focus on the Juno experiment and also talk about the future neutrino instability decay. Yes, I hope I can, in my slides, I can set up the relationship or guide you to think about how you design and develop your technology to achieve your scientific goal. Okay, so I start from the 4 lessons by Weinberg. This is a Nature paper, and there are 4 good lessons. So first is no one knows everything. So if you have something you don't know, it's not a shame. And while swimming, and if you are not dying or not sinking, you should aim for rough water. So we have a good example yesterday. We swim in the wild lake, Lake Baikal, and Jianglai is the person who is energetic and young enough and to aim for the wild water, and I think this is something we should also keep in our life. And you can forgive yourself for wasting some of time to think about some difficult problems, big questions. So it will inspire you for the future. And the last is that you should learn something about the history of science, at least in your field, the history of the previous genius scientists, how they do their study, how they reach our current level. So in the next few slides, I will show some history about neutrino studies. Well, actually, the neutrino study starts from the 1930s, but the whole story starts from probably 1910, where when the Rutherford discovered the structure of the atomic, and well, in that age, he first discovered the the alpha ray is the alpha particle, and the beta ray is the electron, and the gamma ray, etc. So in 1919, he used the polonium alpha source to heat the gold foil and measured the backscattering of the alpha and study the and understand the atomic structure of the nuclei. And then people start to use the radioactive sources to study the inside structure of nuclei. And soon people found that in this carbon decay, there's some display issue. In the carbon decay, you should expect monoenergetic peak, but you observe the continuous spectrum. So this causes a crisis on energy conservation. And also the spin looks like it's not conserved. And this is caused many years confusion or trouble in the field. If you look at closely to this two-body process, you can simply do this calculation according to the kinematics, and you will realize that if it's two-body decay, the electron energy will be monoenergetic. But actually, when Chadwick observed this decay process, and he measured the continuous spectrum of this beta particle. So this people ask a question whether the energy is long conserved. So at that time, Niels Bohr, a big scientist, he seems don't have the face of energy conservation. He even think about in this microscopic process like beta decay, he suspected the energy may be not conserved. But Pauli is the person who have a strong face in the energy conservation, and he proposed that there might exist another neutral particle. He called it neutrons, which can solve this problem. I will explain later. And this whole idea came out in a letter he sent to the expert at a conference on radioactivity in Tübingen, and this is a letter title. So what's in the content? He proposed a disparate remedy to save this issue, the crisis. So he introduced a neutral particle. He called it a neutron. And this particle has no charge, spin 1/2, and has a very small very small mass, much smaller, like less than 1% of a proton. And by introducing this particle, it can successfully save the energy conservation. So the two-body decay becomes three-body. So in this case, will actually cause a long monoenergetic peak of electron. And also, since this new particle is a half spin, so it will automatically solve the spin crisis. So before you introduce this neutron, the left is the integer and the right is half. So it's not conserved. So this clever idea was in this letter, but he never published a paper about this, just letter. So Pauli is a great scientist. He's reluctant to publish some papers, but nevertheless, he have this great idea. But he also admits that the probability to measure these so-called neutrons is very small. He thinks that if it exists, it will be discovered way ago. So he seems not so believe in this so-called neutron particle. But he put this question to the experimentalists, ask them to test his hypothesis. And we all know that to do experiments, you can really test the correctness of the certain theory. But himself was not a participant in this important conference because he's going to go dancing activity which takes place in Zurich. Okay, so this is the whole story. And then later on, in a famous Solvay conference in 1933, there are two big discoveries that year before this conference. One is the real neutron discovered by James Chadwick. This is the real neutron, the same neutron as we know now. And the positron discovered in cosmic ray measurement by Anderson. So this is the first time we found the existence of the antimatter in the nature. So later on, Fermi, who really named this neutrino, well, you know, Italian language that INO means small. So neutron, small neutron is a neutrino. So neutrino is named by Fermi. And I forgot to mention that in the positron discovery, a Chinese scientist, Chongyao Zhao, has worked together with Anderson, has made an important contribution to the positron discovery. So now people start to hunt neutrinos. So after the hypothesis proposed by Pauli, Fermi bring together three novel ideas. So one is the neutrino proposed by Pauli, another is the production and the annihilation operator by Dirac, and also the isospin theory by Heisenberg. So he put this together to produce the effective beta decay theory like this. So this theory is very simple. The beta decay can be explained by the interaction of the lepton current and also the nucleon current. And probably this is the most important theory work by Fermi. And he calculates the, but this theory is so advanced, he submitted to Nature, but Nature rejected. So later on, Bate and Pierce, they think about how to experimentally detect the neutrino, and they proposed this inverse beta decay, very classical process. And in this process, the neutrino will be produced, neutrino will interact with proton and produce a positron plus neutron. And he did a very simple calculation based on the dimensions. And the result is that the cross-section is very small. So it's very difficult to measure. And this paper got accepted by Nature. And then Bate seems not quite believe in neutrinos because based on his calculation, the cross-section is so small, it's very difficult to measure. So in his famous paper, to explain why the sun is shining, in all these reactions, neutrinos are totally ignored in all this. So again, now we know it's not right, but it does not hurt his great contribution on this on explaining why sun is shining, and this paper led him to the Nobel Prize. Then in the 1950s, people think like Raynes start to think about whether we can use a nuclear bomb to detect neutrinos, because the nuclear bomb will produce a lot of neutrinos. And this is the schematic design of this idea. If you blow the nuclear bomb here and you have an underground detector here, you measure it. But this is not safe. So Fermi proposed another safe way to use the artificial nuclear reactors to measure the neutrinos. And here I want to mention another suggestion. In 1942, Kanchang Wang is a very famous scientist in China. He worked as a Dubna and was elected as the vice president in 1956. So in this paper, in 1940s, he proposed another way to also a two-body interaction to detect the neutrino. So this eta is the neutrino. So here, with the help of my friend Yufeng, he suggests me to leave a homework for you to calculate if neutrinos happen in this direction. Please calculate the recoil energy of the neutrino. So this is a relatively simple exercise for you to practice. And actually, the answer is already in the paper, so you can check whether your answer is the same as Kanchang. Okay. Then in 1940s, 50s, Cohen and Raynes used the reactors at the Savannah River to search for neutrinos. And this experiment has been lasted for a few years. And they also use this classical inverse beta decay reaction. And using a few tons of a liquidinator, they finally detect neutrinos in 1956. And they are so excited, and they telegrammed Pauli about their discovery. But Pauli never, well, really, but they did not get prompt reply. Then later, many years later, the Pauli students deliver the feedback telegram from Pauli. Well, actually, Pauli already promptly replied, but the telegram was kind of delayed due to some reason. That's what I heard. Then until end of 1980s, this telegram was delivered to Raynes. And what he said is that, thanks for the message. Everything comes to him who knows how to wait. So this is the discovery. And then another story is that a few years later, Raynes mentioned to Bate, because Bate think it's very difficult or it's impossible to measure neutrinos. So Raynes kind of joked on Bate. Oh, you said that there's no practical way to observe a neutrino. And Bate said, well, you should not believe everything you read in the papers. Okay. Okay, so I will briefly go through the other histories. Like in 1962, the mu-type neutrino was discovered by using accelerators. The proton hit a target and produce pion and kaon. They decay to muon, and muon decay to produce neutrinos. So this is actually the foundation of the current accelerator experiment. This is the principle. And in 2000, the tau neutrino is discovered at Fermilab. Well, a few years later, then this discovery, the solar neutrino also was discovered. This radiochemical reaction was actually proposed by Pontecorvo in 40s. And Ray Davis came up with the experiment with this idea to really measure the neutrino at the home stake. And there's another person which is very important, John Baikal. he did a calculation for solar neutrino flux for 30 years. And Davis' measurement was always compared to Baikal's calculation and to understand the properties of neutrinos. Okay, here's a few milestones in these 30 years after a neutrino was proposed. You all know the Fermi named the neutrino, and he created the beta decay theory. And his genius student, Majorana, he proposed that the neutrino may be its own antiparticle. Now we call it the Majorana neutrino, but this has never been observed. Then in 1957, the parity violation discovered, and very quickly there are many other important theory work, like superconductivity theory came out. All this work led to the two-component neutrino theory. So after the reaction neutrino discovered, Kontokovo first proposed if the neutrino and antineutrino can have an oscillation. This is the first time oscillation concept was proposed. And in 62, the Sakata group has proposed that the flavor conservation may happen between neutrino types. This is right after the new mu type neutrino was discovered. And then I will talk about later that the solar neutrino seems to have missing effect in a solar neutrino experiment. And immediately after this hint, Kontokovo suggested whether there's new E to new mu oscillations and he derived the formulas to explain the oscillation. This is the first time we have the oscillation formula. So all these important series are still now the foundation of our understanding of the neutrinos. Okay, so I quickly go through other properties. The neutrino has only left-handed helicity measured in this type of experiment, and then the number of neutrino types was measured with the Z-wise in the LC experiments, and all these different measurements have a consistent results that neutrino only have neutrino participating in the weaker interaction only has three types. Okay, so back to the step back to the 60s. This is the fusion reaction chain in the sun to explain why the sun is shining and how neutrino is produced. There are many different reactions. And in the first day, when Davis carried out the home-stakes measurement, immediately he realized that the solar neutrinos seems missing. You see this point? And after 30 years, we found that almost two-thirds of solar neutrinos are missed. We don't know why. And actually, at the first day, as I mentioned, Kontokovo suggested that there might have some flavor change or oscillation in this scenario. And then later on, more than 20 years later, Herb Chen proposed a very clever idea, I will also talk about later, to detect to search for the evidence of the flavor transformation for neutrinos using boron-8 neutrinos in the sun. So this boron-8 neutrinos has higher energy. Okay, so in 70s, the grand theory was proposed, and it predicted that proton can decay, and this is the predicted lifetime of a proton. So a few experiments, several hundred ton or 1,000-ton scale experiment was carried out to search for proton decay. But in this measurement, the dominant background was the atmospheric neutrino interaction in the heavy water. And they found that the expected background is much less than, the measured background is less than the expectation. So this is so-called atmospheric neutrino anomaly at that stage. And people start to seriously discuss the oscillations of neutrinos. And this solar neutrino missing problem and or solar neutrino mystery, and also the atmospheric neutrino anomaly, has stimulated a lot of experiments in the late 1990s. And you see there are a lot of experiments using different reactor sources to search for neutrinos. So I'll show you a few examples. So first, atmospheric neutrinos. These neutrinos was produced by the primary cosmic rays interact with the air and produce a shower. And in the shower, there are a lot of kaons, pions, and they decay to produce the neutrino, mu type neutrino and electron type neutrino. And the ratio of these two types is roughly to 2 to 1. Of course, it's kind of energy dependent. And then the superconductor experiment discovered the neutrino oscillation, and this show you the scheme of this experiment. This is a detector, schematic plot, and the neutrino interact with the nuclei and produce a lepton and hadronic processes. And because in water the hadrons are invisible, so what they measure is the final state leptons, and this will produce a chunk of light. And then you measure this chunk of light. Sorry, I should have a plot here, but it does not display anyway. For muon like, it's a good one ring. For electron type, the ring is fuzzle. So using this chunk of ring characteristics, you can distinguish the muon type neutrino and electron type neutrino. And the oscillation signature is that you look for the downgoing neutrinos and compare with the upgoing neutrinos. So you will expect to observe oscillation effect. So this oscillation cycles is due to the different transportation baseline where the neutrinos come from. So in average, you expect to observe a signal like this. The ratio is like 1/2. And this is what you expected, this deficit. But the previous Kamiokande experiment was too small. It's only 3,000 tons. So super K is 50,000 tons. And interestingly, if you know that the Kamiokande experiment is searching for nucleon decay, but it upgraded to super K. It's changed the name to search for neutrino oscillation. It's neutrino detection detector. Okay, yeah. So in 1998, super K reported their results in the neutrino conference, and you see this clear evidence that mu type neutrino has a deficit compared to the Monte Carlo expectation, and the significance is more than 5 sigma. It's 6.2 sigma, and this deficit can be converted into the oscillation parameters. This is delta m square, and this is the oscillation amplitude sine square 2 theta. So you can see here. By that time, this first result, they cannot exclude whether the neutrinos oscillate into a stellar neutrinos. So later on, with more data, they excluded the oscillation into stellar neutrinos, so confirmed that this is the nu mu to nu tau oscillation. So this is a great success in the super K. In snow, as I mentioned, Herb proposed a very clever idea using heavy water to detect the solar neutrino. So I call it one stone, three birds. So what's three birds? So these are the three. So in charge current, it's only sensitive to the electron type neutrino. And for neutral current interaction, in the final state, neutron comes out. So this will be sensitive to all type of neutrinos. Another is the elastic scattering. Again, this is the, through the weak interaction by Z boson exchange, and this process is also sensitive to all type of neutrinos. But the second and the third, they're sensitive to different levels. So basically, you have three equations, and you have three unknown parameters, so easy to solve. So this is the genius idea in this paper. And the Snow experiment discovered the solar neutrino flavor transformation, and this is the schematic plot. I already explained the principle, and since it's heavy water, so again it detected the ring of the electrons, but the electron energy is so small, so it really it's hard to visible. It's hard to see a clear ring, so it's basically measure the energy. And this is the spectrum they measure. This is the final state electron kinetic energy, and this is the charge current, neutral current, and the background spectrum. So this measurement was beautiful. As I said, you have three equations and three unknown parameters. The elastic scattering and the neutral current scattering, they have a different sensitivity to the other type of neutrinos. So you measure the three bands, and they perfectly centered here. So this is the total, this crossing means all these measurements are consistent and matches with the solar model prediction. And what was missing in the previous measurement is that electron neutrinos converted into the other types. So this is strong evidence for the neutrino oscillation. And now I come to the another homework. Probably you need to search more on literature and calculate the oscillation. Oscillation phenomena and all this derivation of the oscillation equations. So I explained the detection principle, and this is the results, the flux from Snow. So the homework is that assume the solar neutrinos are produced at the center of the sun with the electron density of the 100 nucleon per cubic centimeter, and take into account two flavor mixing approximation denoted as theta and the Darm square. So please calculate the survival probability of neutrino flavor conversion of 110 MeV solar neutrino by assuming adiabatic approximation. So there are something I didn't explain in very great detail, but it's up to you to search in the literature and do some exercise. The second problem is that assuming the charge current and neutral current measurements are statistically independent, please derive the best fit and the uncertainty of the mixing angles theta. So this is actually to let you to repeat the measurements of Snow. Okay, so in 90s, other experiments searching for the oscillation, like in reactors, shows experiment and Palo Verde. They attempt to search for the electron antineutrino to another type of neutrino oscillation by using reactors. But of course, due to the limited sensitivity, they have no discovery, and they only provide the allowed region of the theta 1,3 and Darm square. This is the knowledge up to 2002. after the discovery of neutrino oscillation in Super K and the snow, there are many solutions. This is so-called a large mixing angle solution, the small mixing angle solution, and this low Dalton square region, and this vacuum solution. This was how to say chaotic situation at that time. The theorists believe that the neutrino mixing is similar to quarks, because in quarks the mixing is very small. So many theorists believe that the mixing in neutrino sector is also very small. So most of them prefer the small mixing angle solution. So in this situation, the Camden experiment was proposed. So Camden actually is a reactor neutrino experiment. It reused the Kamilka cavern because Kamilka was upgraded to Super K, and this cavern was empty. And Atsuto Suzuki-san proposed this Camden experiment to verify the large angle solution. And luckily, in 2002, it observed the neutrino disappearance in the reactor using the reactor neutrinos. Okay, so this is the first result in their first paper, and then after, okay, so yeah, in this first results, there's evidence. Then after a few years accumulation of data, you can clearly see a nice cycle of this oscillation. Then this large angle solution becomes more clear again as more statistics. So this is result in 2005. You still see some different solution regions, but then in 2008, you only left over this large mixing angle solution. So this Camden experiment is really a lucky experiment and a very successful experiment, which verified the neutrino oscillation and determined this solution. Okay, so a byproduct in Camden was very interesting. It discovered the first observation of the geoneutrinos, because in reactor neutrino oscillation measurement, the geoneutrino is kind of a major background, as you can see here. And use this measurement, we can put the we can verify or check the prediction from the geologist about the thermal power of our Earth. And using neutrino signal, we can put an upper limit of our radiogenic power of the uranium thorium in Earth. And this is will be continue a topic in Juno experiment. I will also cover this. Okay, so a very brief mention about the other accelerator experiments almost during the same time. So K2K confirmed the neutrino, mu-type neutrino oscillation, and the MINOS also supported the measurement by Super K and the K2K. And these experiments are decommissioned. And now the running experiment is T2K from Japan and NOVA from US. They continue running to probe the CP violation using by check the difference between neutrino oscillation and anti-neutrino oscillation. Okay, so this is the status in 2004. We now have almost a clear picture on a three-generation neutrino oscillation picture. And we derived the two sets of oscillation parameters, but only missing one is C13. And so there was a white paper discussed globally about how to measure the C13, and the competition was strong. Sorry, I'm not sure if I was too slow. So the proposal was still using reactors. So why at reactors? So you look at the oscillation formula in reactor and using accelerator, you realize that the oscillation in reactors is very simple. There's no crosstalk with CP violation and the matter effects as here. In the matter effects is A and the CP violation is delta. So we can do a relatively quick measurement and relatively cheap compared to the accelerator experiment. And this is a simple illustration about if you do a measurement using reactors, the oscillation of the electron antineutrino almost equally oscillates into mu type and tau type, as you can see in this bluish and well, dark blue and the light blue region. Okay, so in early 2000s, 2003, something like that, globally there are many proposals to search for C13 oscillation, and 3 out of 8 proposals was finally approved and conducted. This is Data, W, and Reno. So the difficulty to measure C13 is that in the past experiments, the experimental precision is quite poor, a few percent. The dominant factor is in reactor-related systematic errors and also the detector-related systematic errors. So two Russian scientists came out with a clever idea to do the near-far relative measurement, which you can largely cancel these uncertainties and to reach percent level measurement. And all these experiments take this relative measurement approach, but the Data has the better design, much smaller systematics, much higher power, and eventually sensitivity is the best. So here I briefly introduce the neutrinos from reactors. So in reactors, in a commercial reactor core, there are 4 different fission isotopes. So uranium-235 is one of them. So it can have a chain reaction where the neutron can interact with the uranium and produce this complex chain reaction, and the neutrino can be produced. And this is the distribution of the fission products. So based on this process, you can calculate and predict the neutrino flux. So in a typical commercial reactor with 3 gigawatt, the neutrino flux is about 6 times 10 to 20 neutrinos per second. To do a more careful reactor neutrino flux calculation, if you take the pressurized water reactor as an example, the calculation can be like this. So this W is the reactor thermal power provided by the power plant, and F is the fission fraction from the reactor core simulation from their software. I'm sorry that the display has some issues. It does not appear in my laptop anyway. There are 4 isotopes, uranium and 2 uranium and 2 plutonium. As the reactor burning, the fission fraction also evolutes. So you can calculate the spectrum of each fission product, and you correct some effect due to non-equilibrium effect of the fission fragments, and you need also take into account the contribution from spent fuel. So you put all this together, you calculate the flux. And this data nicely shows you measure the flux, how it matches with the prediction. It's even more complex how to calculate how to predict the spectrum and the flux. There are many papers about this, but I just briefly do an overview. There are 2 approaches. One is called summation. It's an ab initio calculation. So you take the database, you take the search for the fission fragments, take out all the chains, all the branches, and you do the ab initio calculation. But this method is very, there are thousands of different branches. It's very difficult to control the systematics. So people use another way to use the conversion method. So in the 80s, EO experiment measured the beta spectrum from the reactor isotope, and we can convert it into the neutrino spectrum by assume a few tenths of virtual allowed decays, and you fit the parameter and like the amplitude and the endpoints, and then you sum them together to predict the neutrino flux and spectrum. And later on, Miner and Huber do another calculation and also include the ab initio calculation. They discovered that there seems to have a rate anomaly and also the spectrum anomaly. And this is a very complex calculations. I'm not an expert. Probably I will skip this and you can search in the literature. The detection of neutrinos, already mentioned, is inverse beta decay. The neutron in the final state can be captured on proton or gadolinium. Gadolinium is the target used in diabase, and the neutrino signal will be the coincidence in time, space, and charge, because this is prompt and delayed coincidence, and also they are from the same vertex, and you have a clear signal region of a prompt and delayed signal. So liquid emitter is a perfect target for this detection. It's cheap, it has rich proton, and it scintillates, so it has a very good energy resolution and easy to handle. And this is a simple formula you can calculate from the positron energy to the neutrino energy. So the diabase experiment is designed like in this way. It's near-far relative measurement. So we have two near sites, one far site. Each site we have multiple detector modules to control the systematics, to cancel the coordinated systematics. In the early time, we even thought about the movable detector. We switch the near and far site to further reduce, but we never did that because the current experiment has already reached a very good precision, and we don't need to take the risk to move the detector. But that was the original idea back to 2003. And we have a redundant muon detector, the RPCs, the Walter-Cherenkov detector, and in the end, we reach a very high efficiency on muons and very small uncertainties. So if you compare the diabase with Reno and double show, first diabase detector was optimized at the right position, the oscillation maximum, and but other two are not. And concerning the background control, the far side of diabase has a higher mountain, which significantly reduced the cosmic ray background. And also the target mass in diabase is much larger than the other two, give you more statistics. And as I said, the identical multiple modules are very useful to do a side-by-side comparison to control the systematics. So in the end, we did a very good measurement, but before diabase, this is very bad. Okay, so the information here is that back to 2011, I think Jiang Lei and Dimitri well know this history. Right before diabase to take full-size data, there was hint from other measurements, like T2K, Minos, and double show. They all have a hint at 1 to 2 sigma level, and but which already warn us that theta 1 probably is not that small. So we have to do it right in diabase. So the strategy is that if the theta 1 is very small, diabase sensitivity is the best, and we have no competition. But if it is large, we have other experiments ongoing, and in principle, each of us can discover non-zero theta 1 3. So we have to be fast. And in this case, starting the far side data digging is critical to reach to this good sensitivity as fast as possible. So in the end, we turn out to have this two-phase approach. Take the all the means to rapidly reach this sensitivity and then do the precision measurement. So this strategy was successful. We use this so-called 2-1-3 layout to carry out our first measurement. And only with 55 days data, we measured the disappearance signal from the reactors. And with 5.2 sigma significance level, we determined the non-zero C213. And this opened the gate for future mass ordering measurements and the lepton CP evaluation measurement. And after almost 10 years running, with the complete data set, we improved the oscillation measurements by a factor of more than 5. And now this is the precision of C213 here, 2.8%, and the Delta square is like 2.3%. And we are now also combining two data sets. One is neutron capture on gadolinium, and another is neutron capture on hydrogen. And this is a global comparison of the oscillation measurement, this C213, compared with the Reno, WSHO, and the T2K NOVA, and that is the best, of course. And this is the Delta square measurement in normal ordering scenario and the inverted ordering scenario. The reactor measurement from Data is comparable to the other measurement. And this is how the precision evolution in the past like 10 years. Now we are here, and we are in the final analysis stage to further improve the precision. Okay, so let me see. Okay, so this is the current understanding of the neutrino oscillations. We have a very complete picture, 3-generation oscillation picture, and the mixing matrix is like this. We determined many parameters, but there are still many unknowns, like a mass ordering, the CP phase, the theta-23 octant, and we need the precise lineage of all these oscillation parameters to test the unitarity of the mixing. How to say? The unitarity of this lepton sector mixing. And this is the current global fit, very new. And this is global fit parameters is, of course, much better than a single experiment measurement. But in any case, this is the precision from this global fit. They are all at a few percent level. So next generation experiments, like Juno, will aim to reach like sub-percent level precision. And of course, we don't know the mass ordering. So I will talk about this in my second part of my lecture. So here is the future oscillation experiments: Juno, Hyper-K, and Dune. These two are the accelerator-based experiments. They are all like a few tens kiloton detector, huge detector, very different technology. Hyper-K uses water, classical approach. Dune used the liquid argon, which is very fancy, very complex technology, many challenges. And Juno used the liquid resonator. So I will cover this in my next talk. So I will briefly introduce these two. So for long baseline accelerated experiments, the principle is simple. I use this diagram to explain. The proton hit the beryllium target to produce, again, the kaon and the pion, and they decay in a pipe, a decay tunnel to convert it into muon-type neutrinos. And nowadays, people use the off-axis alignment to tune the energy spectrum of the neutrino. So if you put detector at the off axis, you will narrow your energy spectrum to the lower energy region. So in that case, you can optimize your oscillation measurements to put your detector at the maximum oscillation location, so you can maximize your sensitivity. Now the NOVA and T2K are in operation. Both of them use this off-axis approach, and to measure the neutrino, mu neutrino, and the anti-mu neutrino oscillation to measure the CP violation. The oscillation parameters are mainly determined from the disappearance channel, and the CP violation is probed in the appearance channel. And this is the complex oscillation formula. As you can see here, it also included the Delta square 3.1 related with the mass ordering and this delta CP item. And it has many crosstalk of different oscillation parameters. And if you do the anti-neutrino oscillation mode, you change the sign of this delta and the mass item, factor item here, and then you compare the oscillation signal. You can extract the neutrino oscillation, you can extract the mass ordering information and the CP information. And here you see this, if the neutrino ordering are normal or inverted, they sit at different locations in this oscillation probability 2D plot. And if delta CP is 0, 2, 0, half pi or pi, is going like a circle in this. So this is the principle of this experiment to measure the mass ordering and the CP. And this is the current results. Both T2K and NOVA slightly favor the normal ordering, as you can see here. The inverted ordering was excluded, but not very significant, like 1 to 2 sigma level. But there's still some tension between these two experiments. Now these two experiments are working together to try to do a combined fit to resolve this tension. But anyway, the current information on CP is not strong, but slightly normal ordering is preferred. The future in US, doing experiments, I want to read all the parameters. They use a megawatt neutrino beam shoot to, both of these two experiments, megawatt neutrino beam shoot to the a few tens of a kiloton detector and measure the CP and mass ordering. So compare these two. The neutrino beam from J-Park to Hyper-K, the beam power is slightly less, but the target mass of Hyper-K is slightly larger. So in this case, the Hyper-K has slightly better sensitivity on CP violation, but the baseline of dune is much longer. The matter effects is large, so they have much better sensitivity in neutrino mass ordering. And the spectrum of the neutrino energy is sort of different. For Hyper-K, the energy is smaller in the lower energy region, and the distribution is not wide, it's narrow. While for dune case, it's wider and higher energy. And to detect these GV neutrinos is very complex, and this is a cross-section of this GV neutrino interact with the nucleon target. You see the measurement is not many, and prediction has a large uncertainty. The major process is still the charge current and neutral current. The difficulty is to measure the final states hadrons. The lepton is simple. You can measure it in liquid argon and in water. It's very simple. But the hadronic processes is very difficult. So to identify the final states, to do the flavor identification of neutrinos and also the neutrino anti-neutrino discrimination is a challenge in both in water and in argon. And you also need a very precise measurement of energy so that you can use this L/E formula to measure the oscillation parameters. This I already mentioned. This is another diagram to show you the Cherenkov process to measure the neutrinos. It's simple that the charged particle goes through the medium and produces Cherenkov light. For muons, it's very straight, very nice ring. But for electrons, the scattering is more significant. So the direction changes during its propagation, and the ring is fuzzle. For pion, pi 0 decay to 2 gamma, and 2 gamma produce electron, compounding electron, and they produce 2 rings. These 2 rings are even more fuzzle. So this is the principle in water. And the key factor is that you need, like a super K, a dense, an array of PMTs to measure this ring. You see this example. This is a non-shower ring and this shower ring. The efficiency, you want to improve your detection efficiency. The PMT efficiency is the key factor, and you need to have no PMT dark noise to reduce the random coincidence signal. And if I'm not mistaken, that Super K ran their detector at 4 degrees, which caused a very low temperature environment. The dark noise is very low, probably similar in Hyper K. And the water transparency is much longer, it's like close to 100 meters. And neutron tagging is also very important to detect the final state neutrons to be able to do the PID for electron type and the new type neutrino. These are the parameters compare between Super K and Hyper K. Hyper K have more PMTs, slightly lower, a factor of 2 lower coverage, but the other parameters are almost the same. So the experience from Super K is extremely important for Hyper K. For liquid argon TPC, well, the principle is simple. The charged particle can ionize the argon, and the ionized electron will drift from the interaction point to the end of the wire planes. So in a kiloton scale detector, the drift length is long, so the drift time is a millisecond level. So in the end, you determine the position of the energy deposit by using the drift time to determine the z, and use the signal in the wire plane to determine the x and y. So in the end, you can do a 3D reconstruction and also a tracking to detect the neutrino interaction processes. And the trigger is using the light, because argon is also a scintillator. Interaction point, it also produces the UV light. And this liquid argon TPC has also a long history. Calrubia, which was also a Nobel laureate due to his contribution to the bosons, Z and W bosons. And he proposed this idea in using the liquid argon TPC to measure the neutrinos. It was a few tens of years history to develop the technology. It's beautiful, but it's very challenging. The beautiful thing is that using this TPC, you can clearly see the final state leptons, gammas, hadrons. It's a very nice 3D tracking detector. But the challenge is that you need long drift distance, stable electric field, You have to put your electronics in code to minimize the noise, and you have to maintain a huge cryostat system for multi-kiloton scale TPC. So Dune collaboration is still working on it. And this is their far detector layout. Two readout technologies. One is so-called horizontal drift here, horizontal drift, and this is the vertical. This is horizontal drift, and this is vertical drift. They are working on the two options, this vertical drift was designed, baseline design for the modules 3 and 4. You know that in Dune they have designed 4 modules. The first 2 will use this horizontal drift design, and the rest of the 2 probably will use this design. And the sensitivity for mass ordering, let me see. This is Hyper-K, this is Dune. For mass ordering, due to a large matter effect, in about a couple of years, if it's full power, then Dune can reach 5 sigma on mass ordering very quickly. But its sensitivity on CP violation is slightly worse than Hyper-K, but not much worse, slightly worse. But concerning time scale, Hyper-K will be in operation in 2028 and 2028, yes. And Dune will complete their detector far detector first in 2029, and then wait for beam to be ready in 2031. So a few years later, Dune will be in operation. So these 2 experiments will hopefully nail down the CP violation problem. A little bit about the atmospheric neutrinos. So Super-K I already mentioned. This is the current status. In the 20 years data set of Super-K, the oscillation study shows that slightly favor than normal ordering, as you can see here. This is the inverted scenario, and this is normal scenario, and the minimum is if you compare the vertical distance of the 2 local minimum, it will give you the significance of mass ordering, not too much. And the joint fit between the Super-K and T2K can exclude the CP conservation close to 2 sigma. Again, not strong. On the other neutrino telescope, like IceCube and Chem3Net, now their measurements on the mass ordering, not mass ordering, the mass square, datum square, is comparable to the other experiment. And with almost 10 years data, IceCube also slightly prefer normal ordering. And the oscillation measurement of Orca, this is the telescope in the Mandarin Sea, they slightly prefer inverted ordering. So there's some slightly tension here. They are continue to run, and but this is the current generation, and of course it will not produce the definitive results on CP. So CP will rely on the future experiment. I would like to mention Baikal experiment since we're here. I asked Dimitri where it's located. Probably it's in southwest, right? From here, right? Southwest. And yesterday I searched the website of Baikal GVD, and looks like this year in April it finished the 14th cluster installation with 8 rings. So you have more statistics, larger size. And interesting is that IHAP is collaborating with Baikal experiment to deploy the prototype for future large neutrino telescope. So this is very nice that we continue our collaboration from neutrino oscillation to neutrino astronomy. And this is the design and the progress of Baikal experiments. And this is the mu-type neutrino flux measurement using the recent data. So it looks very nice. Okay, so this is my last slide for the first lecture. In this talk, I briefly overview the history of neutrino study and the neutrino oscillation study. And you can realize that now we are using all various sources: reactor, the atmospheric neutrino, and man-made accelerator neutrino source to study the properties of neutrinos. We will continue doing this for next probably 20 or 30 years and to deep our understanding of neutrino properties. Okay, so that's my first part. Questions?
Any questions, please?
Okay, thank you for your speech. I have questions, and one first question. So please to 20 second slides.
20 seconds.
What is it? PEP?
PEP.
Yes.
Here?
Yes. What is it?
It's just a kind of a naming of this reaction. This
is
yeah, it's PEP, proton, electron, proton. Yeah. Yeah.
Okay.
The whole chain is complex, so people just name in different directions and according to the neutrino flux.
Okay. Next short questions about what is it experiment in Krasnoyarsk?
I think I heard that. There's a plot. You mean this one, right? This triangle one, Krasnoyarsk. This was, I think, Russian scientists played a very important role in the history of neutrino study. There are a lot of experiments carried out here to search for neutrino oscillation. But due to the small targets, the large background, none of them observed the clear signal.
Okay, here is another question.
Thank you for your lecture. You mentioned that some types of neutrino oscillations are more preferable than the others. So can you explain why, or it's just statistics shows that they happen more frequently than the other ones?
Some neutrino oscillations are preferred. Probably I did not mean that. I think what I mean is that the current experiment data prefers normal ordering of the neutrinos by combining different experiments. I think I did not mean one particular neutrino oscillation is favored than other. All the different oscillation channels are very useful to measure the mass ordering, the CP violation, and oscillation parameters. Just the current experiment, like two accelerator experiment like NOVA, T2K, they slightly prefer normal ordering. And also the super K, atmospheric neutrinos, slightly prefer. So this is the current experimental hints.
Okay. So another questions, please? Yes.
Thank you very much for your very interesting lecture. You mentioned that usually two detectors, neutrino detectors, near and far detectors, and there is the possibility of creating a moving detector. So I'm just wondering, what if we have three detectors? Let's say
Three.
a near detector, far detector, and let's say a middle detector. will it provide any significant improvement in measuring of neutrino mixing parameters?
That's a very good question. I think probably Dima, you remember that in early stage of diode, we did consider the middle detector somewhere in between. And then you can do the sensitivity calculation to put a middle detector, and it can cancel some symptomatics, of course. But then you can also, have to consider cost. We are experimentalists. Our dream is to use the smallest amount of money to do the greatest science. So then you can judge your sensitivity and your experimental cost. In the end, we think it's not worth to do that. The near-far cancellation is good enough. And you also put your 2 near detectors on each side, on each near side, and 4 detectors on far side. In this way, you can well control the systematics. So that's the way. Eventually we end up with the near-far configuration.
Okay, thank you.
Thanks. Next question.
I have a question about, well, first of all, thank you for the lecture.
Thanks.
I have a question about detectors as well. And so we need a far detector, a very sensitive far detector. And can we use, for example, Baikal GVD or Ice Cube as the far detector and direct a beam of neutrinos from like a distant accelerator through the Earth? What difficulties can there be, and is it possible even?
Yeah, I think phenomenologists always discuss these kind of ideas in literature. In principle, if you already have an existing big detector, theorists always consider where I can put another accelerator, shoot the neutrino beam to this huge detector and to study. From scientific point of view, this can be discussed and has been discussed. I can give you another example that Hyper-K and T2K, they have a neutrino beam in J Park in Tokai, in the east coast of Japan. And the Korean scientists are considering to build a second Hyper-K-like detector in Korea. It's called a T2 Hyper-K. T2 Hyper-K, sorry. Probably T2 Hyper-K2, something like that. It's a secondary, second detector, Hyper-K-like detector in Korea. It has a longer baseline, which does have some advantage in science. You put a detector in the second oscillation maximum, and it can have a better sensitivity. But still, you need to balance the effectiveness and the cost, whether it's really worth to put another huge detector further away and to carry out the real experiment. But you can always do this calculation using formulas, and sometimes it does have advantage in science. But in reality, it costs more money, so it's either not approved or just on paper.
Any more questions?
Excuse me for the situation. 55 slide.
55.
Okay. This graphic.
This one?
This graphic. Why of Nova graphic is round and why Baikal is line?
Which one? The circle, you mean the circle one?
Yes, circle and...
Circle one, you see this, there's a small arrow here, which means the CP phase value change, for example, from 0 to half pi to to pi.
Because this is phase. Okay.
Yeah, the phase produce this how to say signature of this circle-like. But in reality, you only have one CP phase. If you do the experiment, you have only one. Then you will determine where.
Четвака is two phase or one.
No, CP phase is just one, but we don't know yet. So this plot show you we kind of scan different values, and it will indicate us if future CP is in this phase, where it locate. So.
Okay, thank you very much.
Yeah, yeah.
Okay. Oh, there's one more question.
Yeah, thank you very much. So I have a question about reactors.
Yes.
You have on a graph or image a lot of them. Yeah, the image with Fresnel yards. So is there
You mean the reactor flux or the experiment? Is this one?
do you use as data collector different kinds of reactor, or they all the same?
You are talking about the difference between different reactors.
Yeah.
Currently, the commercial reactor, most of the commercial reactor is this type, pressurized water reactor. They have very similar operation mode and the design, and the fission products is always this 4, and the fission fraction evolution, as you can see in this plot, the uranium, plutonium, they are in a very similar way. And now the different reactor companies have their own core simulation code, which can allow you to simulate the evolution of the reactors. But because the technology developed, so now we do have a different type of reactors. For example, in Juno, I will talk about in my next talk, we have the Taishan nuclear power plant. This uses a very new technology. And it's a French technology, and then modified version in China. Anyway, the operation mode and the design is different from this type. So in Juno experiment, we put a near detector near Taishan nuclear power plant to monitor its operation, to monitor its neutrino flux, to measure the spectrum, and to compare with the Monte Carlo prediction to better understand the systematic uncertainties of the neutrino spectrum and the flux. So, but that's a very special type of reactor. Probably more than 80% or 90% in the world are this type. So it's well understood in the past decades.
Thank you.
Okay.
Okay.
Thank you for the lecture. My question about Marana theory. So according to Reines and Cohen, a reactor produces antineutrinos. And with Reines and Cohen was one more experiment. It's a Davis experiment with the fluorargon method. And it wasn't successful. But in the home state, this experiment was successful and detected neutrino. So Davis experiment shown that antineutrino not equal neutrino, and why Majorana theory alive after that?
Well, the electron type neutrino is different from electron type antineutrino. That's from the flavor aspect. This antineutrino and the neutrino, in front of it, it has a neutrino electron type, which means it's distinguished from interaction mode. It's categorized in categorized as a flavor. So flavor means if it's only interact with electron lepton, we call it electron type neutrino. If it interacts with the muon type lepton, we call it a mu type neutrino. So this is according to the interaction mode. But what Majorana proposed, if neutrino is its antiparticle, that's from the mass property, I think. It's not the interaction property. Probably Dima can correct me if I'm wrong. If a neutrino is Majorana neutrino in a Lagrangian, you put a separate term with the right-handed neutrino, which is very different from the left-handed neutrino. Now all the interactions are left-handed neutrino. So what Majorana proposes is a totally different one. So the previous measurements distinguish electron type neutrino and the electron type antineutrino. That's totally different from what Majorana discussed. I'm not sure if I answered the question. Dima, you want to comment? I'm not a serious.
Yes, maybe I think you gave partially correct answer. The question is actually very clever because it's very often appears.
Yes. Yeah.
This kind of
I'm not a good
so
answer.
the question is that Majorana suggested that neutrino is identical to antineutrino.
Yes.
On the other hand, there are experiments where we see that if antineutrino was produced, it cannot be detected as neutrino. So why we still talking about Majorana theory? I think it's very logical. And I think it has nothing to do with flavor identification.
Okay.
Imagine we have just one type of neutrino. So the answer is very simple actually. According to the standard model, what is produced as neutrino, and you partially gave it, is left-handed particle. What is produced as antineutrino is right-handed particle. Therefore, if a reactor emits a right-handed antineutrino, it can interact as a right-handed, it could interact as a right-handed neutrino, but actually this is not possible if neutrino mass is zero. If neutrino mass is not zero, then in principle, antineutrino from reactor can be seen in a detector as neutrino in the reactor, but with the probability proportional to the square of mass of neutrino to the energy. And since mass of neutrino is on the level of 0.1 electron volt and energy typically is mega electron volt, so this ratio is 10 to the minus 12 or something. So no neutrino experiment is sensitive to see this effect.
Yes. Majorana neutrino, one precondition is that neutrino have mass. Otherwise it's all Dirac. Yes.
Thank you for your comment. Okay.
I have a small question. When you talk about the normal ordering, maybe you mean the normal hierarchy or not? Yes?
Normal hierarchy, yeah. That's what's older name. But in the next, my next talk, the first page is a plot I will show you that it's unlike the quarks and leptons. The hierarchy signature is so obvious that it's clearly hierarchy structure. But for neutrinos, the mass is so small, we don't really have a hierarchical structure.
Ordering has another sense in quantum field theory. Well, in QFT, yes, but in this community now it's normal ordering.
Yeah, there was a debate like 10 years before, ordering or hierarchy.
Okay. If we have no more questions, please thank our lecturer again.
Thank you.